So today we're simplifying cube roots, which will piggyback right off of our simplifying square roots video from yesterday. Now simplifying cube roots is going to work almost exactly the same way. So if yesterday went well for you, this should go well for you as well. There are still no decimal answers. However, you can use those decimals to check if you want to. If you type your original problem in as well as your answer, it should give you the same decimal. Now there are two methods to do this, just like there were yesterday, and the options are the same. So you can either make a factor tree, which is what we're going to start with. So that's where you're kind of doing the prime factorization, and you want to end with prime numbers. So again, things like 2, 3, 5, 7, you want those things at the end of your branches. Instead of finding pairs of the same factors, today we're finding groups of 3. Okay, it goes right along with cube roots because our numbers are going to be all based around 3 today. Yesterday it was all groups of 2 or pairs. Today it's going to be groups of 3. That's really the only major change. Now, what we're going to do is still put one factor from each group outside of the radical. And if you have more than one number, you still multiply them together. So that whole process is the same. Anything that doesn't have a pair is going to stay underneath that radical symbol. Now we are going to start with this method again because it is more flexible than the next one, and it may feel more comfortable in this particular lesson, just as a heads up. All right, so if we start with the cube root of 24, okay, this one again is more flexible. I can choose whatever I want, two things that will multiply to be 24. My gut says 4 and 6. All right, from there, I'm going to break this down into 2 and 2, and 6 will break down into 2 and 3. So now instead of finding pairs like we did yesterday, we're finding groups of 3 of the same number. So I have a 2 that is my group of 3. So that 2 is going to come on the outside, and the 3 that is unpaired stays underneath the radical symbol. Okay, so very similar to what we did yesterday. All right, what you will notice in this section is that the numbers get a lot bigger. So 108. Okay, if you're not initially sure what 108 will break into, start dividing by things. So like I know this is an even number, so I know 2 will divide evenly into 108. In fact, it's going to be 2 and 54. Then 54 is something that I know. I know that that's going to be 9 and 6. 9 will break into 3 and 3. 6 will break into 3 and 2. Right, so I have a group of 3 3s. I also have 2 unpaired 2s. Normally that would create another pair, but now we're looking for groups of 3, and we don't have a third 2 to make that work. So I'll have a 3 on the outside this time, and those 2 lonely 2s will get put back together on the inside. So those will get multiplied to make my answer 3 cube roots of 4. Feels a little strange to have a 4 underneath of a radical symbol, but because it's a cube root, 4 is not a perfect cube, so we can't simplify that anymore. All right, and like I said, the numbers get really big, so we have 5,103. Yikes. All right, now this is an odd number, so I know 2 won't work. You could grab a calculator and start dividing by things, so I'm going to start with 3. 3 actually does go into this, and the number that I get is 1,701 of all things. Still not familiar with that number. Again, it's odd, so I'm going to skip over 2 and try 3, which does work. I get 567. Still not real familiar with that. Odd again, so we'll try dividing by 3, 189. And I'm just going to keep dividing until I get to numbers that I am more familiar with, like this one. This will end up being 3 and 63. Now 63, I know that one. That's going to be 9 and 7. And 9 will turn into 3 and 3. Okay, shoot, finally at the end of all those branches. So now we're finding groups of 3. So here's a group of 3 3s. And actually another group of 3 3s. All right, and then we have a lone 7 there at the end of the branch. So on the outside, I'm going to have a 3 from the first group, a 3 from the second group, and then that's 7, which will land on the inside. And then I can multiply these two things back together to give me 9. All right, and that makes this my final answer. Now, just like yesterday, this one also has a shorthand method, and that's to look for perfect cubes. Now, most people are less familiar with their perfect cubes than they are their perfect squares, so a lot of people don't like this method just because they're less familiar with this list. So you still determine the biggest perfect cube that divides evenly into your radicand. Again, if you don't choose the biggest perfect cube, your answer will be simplified, but not in the simplest form that it can be in. Then we take the cube root of the perfect cube part, and that number is going to go outside the radical. Whatever other number that was paired with that is going to stay underneath the radical. Now, again, just like yesterday, it is more particular what you choose. So I need to make sure that one of the numbers that I pick as for my pair has to be something on this list. 1, again, really isn't going to be used. It doesn't change your number at all, so it's not really all that helpful. So for 24, I know that 8 divides evenly into 24. You're going to use these first few pretty frequently. Occasionally, you'll get some of these bigger ones. 1,000s tends to be pretty easy to see, but for 24, we need 8. So this is going to break into 8 times 3. All right, now similar to yesterday, I can take the cube root of 8, and that's going to give me 2. Remember, cube roots work like similar to square roots, but it's the number that you take times itself 3 times. So 2 times 2 times 2 is what gives us 8, which makes the cube root of 8 2. But if I try to take the cube root of 3, that's going to give me some sort of decimal, which we already said are no good as part of my final answer. So what that allows me to do is to take the cube root of 8, which is 2, and I'm not allowed to do the cube root of 3, so that chunk has to stay the way it is. Now you notice you get the same answer as we did over here. Use whichever method you prefer, which one you feel is easier to understand. Okay, 108, again, not real sure about it as like, I'm not as familiar with it as you might be, and that's cool. But 108 is actually going to turn into 64 times 2. Oh, sorry, 27 times 4. I was going to say over here 2 times 54. That's not quite right. But anyways, 27 times 4. So the cube root of 27 is going to make 3. And we aren't allowed to do the cube root of 4 because it'll be a decimal. So I'm cube rooting the part that I can and just leaving the other part the same. All right, so this again especially gets tricky because it's hard to know what perfect cube goes into this number. It's pretty big. You can start dividing, so I could do 5,103 divided by 8, then try to divide by 27, divided by 64, and kind of work my way up that perfect cube list if you want to. But remember, the first thing that you get might not be the biggest perfect cube, so it is important to keep checking what you get, because 27 will divide evenly into 5,103, but it's not the biggest perfect cube that works. It's actually going to be 729. So the cube root of 729 actually is 9. The cube root of 7 is decimal. So whenever I go to build my final answer, the cube root of 729 is 9, and that goes on the outside, and that 7 is stuck on the inside. All right, other things that can happen, again, is just that having that number out in the front. And again, those numbers are going to hang out until the very end. To simplify the actual cube root part, you can use whichever method you prefer. So I'll do the first one using the factor tree, where we just break this into whatever you see fit. So 625, I just divide by 5 first, so 5 and 125. 125 divided by 5 is 25, and 25 also breaks into 5s. So lots of 5s going on. I need a group of 3. So this 5 is coming on the outside from the group, and then the lone 5 is what's stuck on the inside. Again, not quite finished. This 4 is going to swoop in here at the end and get multiplied there on the outside to make 20 cube roots of 5. And that's actually my final answer. Negatives can actually happen on the inside of cube roots now, but I'm still going to keep it on the outside here, just for the sake of example. You don't see them on the inside too often, but it is possible. All right, on this one, I'm going to use the perfect cube method. So if I break down 375, that's going to turn into 125 times 3, 125 being the perfect cube. So the cube root of 125 is 5. This 3 is coming down here on the inside. And then last but not least, this negative 7 is going to swoop down on the outside and multiply, making negative 35 cube roots of 3, my final answer. Okay, again, because this is algebra, we do have to involve variables here. So I'm going to switch pages. We're going to talk about just the variables for a minute. It's going to work really similar to yesterday's stuff, where we're going to divide, or we can write it all out and find groups. Just again, this is all going to be based around 3. So again, do not cube root an exponent. Just like you can't square root an exponent, you can't cube root one either. Okay, again, there are going to be 2 methods. So it's kind of like the finding the groups, or we can use division to make that work too. So you can write the term without an exponent and find groups of 3. Now, however many groups you have becomes the exponent on the outside. And anything without a group is going to end up staying underneath the radical. So like for this first one, we have 10 x's. And I'm going to find groups of 3. So it looks like we have a group here, 2, 3. So actually 3 groups of 3. So that tells me I'm going to have an x to the 3rd on the outside because there's 1, 2, 3 groups. So that makes that 3 there. I do have one ungrouped x, and that stays underneath this radical symbol. All right, sometimes it does work out evenly. So if I end up with 6 x's and I'm finding groups of 3, I end up with 2 x's outside of the radical and none in. I have no unpaired terms. All right, again, the downside about this method is having to write out a ton of x's, like 17. Whew. All right, so groups of 3. Okay, so it looks like I have 1, 2, 3, 4, 5 groups of 3, making the 5 on the x outside. And this time I actually have 2 ungrouped x's, and that's okay in this case because we're dividing by 3 and finding groups of 3. So I'm actually going to have x squared on the inside. If this number is 3 or larger, you can take another group of 3 out. All right, a lot of people like the faster way for this option, and that's, again, to divide the exponent by the index, which is now changed. For square roots, it was 2, but because we're doing cube roots, we're looking at 3. So, again, your whole number portion from that division becomes the exponent on the outside, and any remainder is going to be the exponent on your radical inside. Okay, so now, if I take 10 divided by 3, 3 goes into 10 3 times. So that's going to give me a remainder of 1. So this 3 becomes the exponent on the outside, and this 1 becomes the exponent on the inside. You can write it if you want to, but typically you won't see it. All right, again, similar to over when we were finding groups, things can divide in there evenly and have no remainder. So that just means I'm going to have x squared. All right, and again, you can see that remainder of 2 here happening in action. So 3 will go into 17 5 times and give me that remainder of 2. So 5 becomes the exponent on the outside, 2 becomes the exponent on the inside. All right, just like yesterday, we can wrap all that together, and the process for this is the same as well. You can still separate each piece. And we're going to simplify those using whatever your preferred method is, whether you prefer factor trees and then using the division, or if you like the factor trees and writing it out, or if you like finding the perfect cubes. You do you, whatever you prefer. Once you get all those small answers, we combine them into one big final answer. Okay, so on this first one, I'm going to split this apart. I have the cube root of 81. And then I also have the cube root of x to the 5th. Okay, I'm going to do this one using the whole break it apart kind of ideas, so the tree and writing out my x's. And then the other ones I'll use the perfect cube kind of method. All right, so I'm going to start with 81, and we're going to break that apart as far as we can. I know that 9 times 9 is 81, and then 9 will break down again into all kinds of 3's. So again, I'm looking for groups of 3, so we have 3 3's. So this group will create a 3 on the outside. This lone 3 will create a 3 on the inside. Okay, so that's part of my answer. All right, over here, x to the 5th means that I have 5 x's going on, and I'm looking for groups of 3. So I have one group of 3 x's, so that one x is going to come out. And then I have 2 ungrouped x's, which will stay on the inside of the radical, so x2. So these are the 2 chunks that I'm going to combine to make my final answer. Okay, just like with simplifying square roots, anything on the outside is going to go together on the outside. So the 3 and the x. Then we have the cube root symbol, and then we have another 3, and then the x squared from the inside here. Just kind of rewriting them together. All right, if I move on to the next one, we have the cube root of 40, so I'm breaking it all apart. The cube root of x to the 9th. And also the cube root of y to the 7th. All right, so on this one, I'm going to look for the biggest perfect cube that divides evenly into 40, and that happens to be 8 times 5. All right, the cube root of 8 is 2. And the cube root of 5 I can't do because that would be a decimal, so that part just comes down. All right, on the next chunk, I would need to do 9 divided by 3. That goes in 3 times, with actually no remainder. So that means I'm just going to have x to the 3rd as part of my answer. All right, for the y's, I have to divide 7 by 3. That'll go in 2 times with a remainder of 1. So that means I'll have 2 y's outside and a single y on the inside. So these are the 3 chunks that I'm going to combine to make my final answer. So we'll have 2 x to the 3rd y squared. And we'll have that cube root symbol. The 5 right there. This part, the x's aren't going to contribute anything to the inside. There's nothing underneath the radical, but the y will. Looks something like that. And that makes my final answer. All right, one more big one. And this one kind of tackles all the things that can happen there. You have the number outside, your big number underneath of the radical symbol, and then 3 variables going on. Whew. All right, I'm going to save that 7 on the outside till the very end. And first I'm going to start with 6,000 by separating everything apart here. Get x to the 14th. Y to the 3rd. And z to the 4th. All right, so 6,000, I need the biggest perfect square that goes into 6,000. It's going to be 1,000 times 6. All right, cube root of 1,000 is 10. 6's cube root is a decimal, so it becomes the radicand. All right, for my variables, remember we're dividing by 3. So 3 goes into 14, I think 4 times. That'll give me 12, and a remainder of 2. So that means 4 x's on the outside, and 2 x's on the inside. All right, this one's pretty nice and smooth. 3 divided by 3 is just 1. No remainder on that one. So we'll just have a plain y. All right, last but not least, we're taking 4 and dividing it by 3. Also goes in 1 time, but this time we have a remainder of 1. So that means we have 1z on the outside and 1z on the inside. All right, we have a lot of putting back together to do here. So I have a 10 and x to the 4th, a y, and a z on the outside. Shoo. Okay, we'll keep that cube root symbol. All right, and then we work on all the inside stuff. So 6 and x squared and a z. All right, still not finished, which is crazy. We still have the 7 up here to deal with. So that 7 is going to swoop on down and just get multiplied here on the outside. It's not a good looking 7. Wow. Okay, so 7 times 10 is 70. And everything else will end up staying exactly the same. To make your final answer. right? The only weird things that can happen, again, really similar to yesterday, if you're breaking things apart and you end up with no groups or no perfect cubes that you can find, like 42 will break into 6 and 7, 2 and 3, so there's no groups of 3. And if you're thinking about your x's, you only have 2, so you can't make a full group of 3. This is actually your final answer. There's nothing that you can do to simplify that any further. Now, if you only get groups or perfect cubes, 512 is a perfect cube itself, and that gives you 8. If I take that 12 from the exponent and divide it by 3, I get 4 with no remainder. So that just means x to the 4th. So I would take these two pieces and put those together and just get x to the 4th without any cube root symbol at all. And that's okay. It just means what you were looking at is a perfect cube.